So thanks everybody for surviving till the last day of lectures, or at least the formal lectures. And we're very happy to have Yifan giving us the last and third lecture now. And again, feel free to ask questions, unmute yourself or write in the chat and ask a lot of questions. Okay, please, Yifan.
Okay, thanks, Shlomo. Thanks everybody who tuned in for the last lecture. So in this lecture, we'll be talking about various aspects of 5-dimensional and 6-dimensional CFDs. So last time I told you briefly about the effective field theory that's associated with 5D superconformal fixed point upon some massive deformations. In this lecture, I'll first tell you about how to go upwards in RG to construct or identify potential conformal field theory from some effective field theory that satisfy a certain criterion. Okay. So the goal here will be to look for, so you can write down some arbitrary 5-dimensional effective theory with arbitrary gauge rule coupled to matter. The goal here is to cook up some criteria that's physically motivated that would tell you that there's a UV completion given by SCFD, okay, potentially upon mass deformation. So just to remind ourselves, the 5-dimensional Coulomb branch effective theory is highly constrained by supersymmetry and gauge invariance. It's determined to be at 2 derivative level is determined by a so-called prepotential, which is a cubic polynomial in the into one vector superfield, which are labeled by phi here. So these first two terms are the classical contribution, which, for example, comes from the non-abelian gauge theory. And the other terms are one-loop contributions that come from integrating out massive W bosons or massive hypermultiplets on the Coulomb branch. So I'll label this, I'll refer to this one-loop effective prepotential as star later in this talk, in this lecture. You can extract the effective coupling for the photon or the U1 gauge fields on this Coulomb branch by taking 2 derivatives with respect to this superfield, as you may have remembered from the 14U2 story. The difference here is that in 5D, the gauge field, the gauge coupling is just real. There's no complex theta angle. And so it just takes this following form. What I want to emphasize here is this minus sign, which originates from the contribution from the massive hypermultiplets to this one loop prepotential. This minus sign may worry you because on the left hand side we have some coupling that's supposed to be positive, but this minus sign may mean that it's actually negative for sufficiently large NF. Okay. So that's a sign where the effective field theory will become sick because it's a basic violation of unitarity, and that means that this theory cannot hold at arbitrary energy scale. Okay, and with that philosophy in mind, Intriligator, Morrison, and Seiberg made the following criteria for a EFT to have a UV completion given by a superconformal field theory in 5 dimensions. That is to require for the general prepotential, which is a function of various U1 superfields phi, you require this matrix with respect to 2 derivatives to be positive definite on the entire Coulomb branch, away from potential walls where W boson and hypermultiplets become massless. Okay, and with this criterion, you can easily see that if you look at this equation for the SU2 case, NF has to be bounded from above, because if NF is too big, there are always some value of phi such that the right-hand side becomes negative, okay? And from this, you can conclude, you can carry out the analysis as an exercise, that this criterion will tell you that NF is bounded above by 7 in order to have a positive definite gauge coupling. And this give rise to this SCFDs, proposed SCFDs, which are known as the ENF plus 1 SCFDs. This label ENF plus 1 denotes the enhanced global symmetry associated with the superconformal fixed point, which we'll say more things about later. And this is just a EFT approach that says that this fixed point can exist, but this fixed point do exist, and this is coming from some later top-down construction coming from M-theory, which we will talk about later. Okay, but here I just want to emphasize that people have long suspected that this constraint is too restrictive. Okay, because this would rule out quiver gauge theories. Okay, and it leads to a very small class of possible 5D into 1 theories. Okay, so to see that as example, let's look at the simplest quiver gauge theory in 5 dimensions and see what property of this quiver gauge theory makes us violate this condition. Okay, to have a UV fixed point in 5 dimensions. So this quiver gauge theory has two SU2 gauge groups, and it's coupled together by a single bifundamental hypermultiplet. From this general formula, you can derive this prepotential. That's a function of two U1 gauge fields. Sorry, the two U1 5D into 1 superfields, vector superfields, which are denotes the two. Correspond to the two cartens of the two SU2s. Okay. And for simplicity, let's focus on the case when we do not turn on any mass deformation. Okay, for this bifundamental hyper, there's a extra U1 you can turn on, but let's turn it off. And then the prepotential, it takes the following form. This is the classical piece, quadratic piece, the classical piece. There's no transcendence level, so there's no classical cubic piece, but there's a quantum one loop contribution. Sorry, yes.
There is a question. Is the global symmetry enhanced only for NF equals 5, 6, and 7?
No. Well, we'll see how it enhances later. Yes.
But you're saying that it's ENF plus 1. So that's like E6, E7, E8. What is it for the other values of NF?
We'll see. For example, E5 is SO10, and in the IR you only see U1 times SO8, for example.
Oh, okay.
And the E4 is SU5, and you only see U1 times SO6. Yeah,
okay.
Things like that. All right. Yeah, feel free to ask questions. Okay, let me monitor the chat. Okay, yeah, I think Dave Morrison answered my question also in the chat. Okay, thank you. So where was I? Okay, so I was saying that this is the contribution coming from the integrating out the massive W bosons, the first two guys, and then this is the contribution coming from integrating out the massive hypermultiplet, bifundamental hypermultiplet. Okay. And then by taking derivatives, you can compute this Hessian, which essentially give you this matrix that give you the effective gauge coupling on the Coulomb branch. And then you can ask, is this 2x2 matrix positive definite? And that's essentially the condition here. And you can easily convince yourself that if you take the strong coupling limit, this is just one regime to test this. If you take strongly coupled limit, you can easily see the trace will be positive because it'll be dominant. You can see the trace is positive if you focus on the branch where phi. I should have read it. You can focus on the branch where phi1 is bigger than phi2. Okay. But the determinant of this matrix can be negative for sufficiently large phi1. Okay. So it seems that according to the original IMS criteria, this fails in the sense that it's not going to be a consistent Coulomb branch that's associated with the superconformal fixed point in the UV. But that's a problematic claim. Why? Thanks to Fabio's lecture, there's a PQ5 brane realization of the same theory as follows. Okay, so remember, these are the PQ5 brane diagram associated with NS5 and D5 branes. And in this brane diagram, the Coulomb branch parameters are associated with the Coulomb branch vectors are associated with the distance between these 5 branes, this vertical direction. And as Fabio mentioned, there are different but physically equivalent descriptions of the same 5D superconformal field theory, but with different PQ5 brane web, thanks to the SL2Z duality. Okay, And in this case, if you act by S-duality, which essentially rotates the diagram by 90 degrees, you get this other brane diagram. And from this general procedure that associates the gauge theory to the brane diagram, once you blow up various faces, this brane diagram will correspond to SU3 coupled to 2 fundamental hypermultiplets. But as an exercise, you can easily check that for this theory, if you do the same analysis, compute its prepotential and compute its effective coupling, it's manifestly positive. Okay. So then we have a contradiction because, as we said, these two are supposed to describe the same physical theory. But in one case, the effective theory that you read out from the brane diagram is perfectly good. It satisfies the AMA's condition, but the other doesn't. Okay, so what went wrong? Okay, so there's something that went wrong from the EFT analysis. The problem was that we trust the EFT analysis too much. Okay, we trusted beyond the regime where it can be trusted. So the caveat that we forgot in this analysis was that this star, the quantum prepotential, which keep track of how perturbative particles become massless, like W bosons and hypermultiplets, but it doesn't quite keep track of how non-perturbative particles become massless. Okay. So those could give rise to additional constraints on where the validity of the effective theory ends, coming from, you can think about as non-perturbative walls where non-perturbative particles become massless. And the notion of perturbative versus non-perturbative it's not a physical distinction if you're coming from, say, PQ5 brane description or M theory description. That's why this picture would not know about this effective theory subtleties. Everything is equivalent. So because non-perturbative states are important, let's remember what kind of non-perturbative states are there in the 5D into 1 theory. So recall that in 4D into 2, we have on the Coulomb branch of 4D into 2, we have monopoles, or multiple dions in general, which are electromagnetic dual of the fundamental perturbative particles, electrons, in a given EFT description. Because of the similarity between the 5D Coulomb branch and the 4D Coulomb branch, here you also have some you also have the electromagnetic dual of the basic hypermultiplets, electrically charged hypermultiplets. And because of the increasing dimension, now instead of particles, you have multiple strings. And similarly to how the mass and charge of the monopole, BPS monopole is related to the mass and charge of the BPS electron in 4 dimensions. The tension of the monopole string is also determined by a derivative of the prepotential with respect to this Coulomb branch parameter phi. Okay, and the non-perturbative nature can be made obvious by noticing that it's proportional to 1 over the effective coupling G squared times some Coulomb branch parameter. Okay, this schematically it looks like follows. But 5D into 1 also has another kind of non-perturbative particles, okay, which is in some sense more mysterious from the effective theory description, that are instanton particles. These are particles charged under the topological U1 symmetry, whose current correspond to the Hodge dual of F wedge F. Okay, and these instanton particles are mysterious because they're not always captured by the EFT, unless you choose the right frame. Okay, like this S-duality frame. Okay, so there's a small exercise that is for you to work out the central extension of 5D into 1 supersymmetry algebras and figure out what kind of supersymmetry is preserved by multiple strings. Okay. You should find out that preserved, for example, 0,4 supersymmetry on the worksheet of the string. Okay, so that's about some review of the non-perturbative states. And as we mentioned, typically when you have this massive states whose mass depend on the Coulomb branch parameter, and if these massive states become massless, it creates singularity on the Coulomb branch, just like what happens in 4 dimensions. Here, this non-perturbative objects, the monopole string, and also the instanton particles can become tensionless or massless somewhere on the Coulomb branch. And this is where the effective description coming from this 1 loop prepotential would break down. Okay. And as explained in this very nice paper by these authors, once this happens, it means that you have to introduce because your EFT is supposed to be a description of low energy degrees of freedom. And if there are extra degrees of freedom, low energy light degrees of freedom, you need to modify your EFT to include them. Okay. So this means that beyond this point, typically you would have a new emergent effective field theory description. So let's apply this kind of perspective to the case that we looked at, namely in the SU2 times SU2 quiver gauge theory. In that case, so as always happens, the prepotential does encode information about the multiple string tension. Although the instantons are mysterious, but the multiple string tension is encoded just by the first derivative of the prepotential with respect to the Coulomb branch parameter. Okay, and from this formula, you can easily compute this multiple string tension. It looks like follows. Okay, and you can also see that in the strong coupling limit, where this gauge couplings are large, which correspond to closer to the fixed point. Remember, 1/g² parameterized the mass deformation away from the fixed point. So the strong coupling means close to the fixed point. You see that as T2 approached 0 from above, as phi1 approached 2 phi2 from below, T2 would approach 0 and from above, and eventually becomes negative. Okay, and I just want to emphasize this is far before phi1 reach 4 phi2, where the gauge coupling, effective gauge coupling, becomes negative. Okay, so just to put this in a more clearer perspective, let's have this simple diagram. So this line parameterizes the phi1, one of the Coulomb branch web. Phi1 is bigger than phi2 in the particular wedge we're looking at, meaning that in the particular wedge we're looking at, okay, and the boundary where W bosons become can become massless. So phi1 is bigger than phi2 in this wedge, and as we increase phi1, what happens is that there are tensionless multiple string as well as massless instantons that happens around 2 phi2. Okay, and this is before where the effective coupling becomes non-positive definite, which happens around 4 phi2. Okay, and recall that the quiver gauge theory description, we trusted too much the quiver gauge theory description because we trusted it on this region, but we're only supposed to trust it in this region because beyond this point, there are extra massless degrees of freedom coming from this tensionless string and instanton and massless instanton that we need to take into account. Okay, so there's no contradiction if we don't trust this EFT beyond this point. But what can we trust beyond this point? The correct EFT description beyond this point is given by this SU3, the effective field description coming from SU3 coupled to 2 fundamental hypermultiplets. Okay, and in particular, the instanton particles that become massless here will be part of the vector multiplets in SU3. So it becomes like W bosons. This is how non-perturbative states can be treated perturbatively in another description, and hence the effective field theory description, which is like perturbative in nature, can capture the correct Coulomb branch dynamics of a CFT. Okay, so with this kind of example, there are many examples like this, and people discuss this example in various ways, but it was only recently systematically characterized as a new criterion for a consistent EFT that has a SCFT UV completion. Okay, this is again this nice work. So instead of applying the IMS criterion for the entire Coulomb branch within a given perturbative wedge, completely within a perturbative wedge, these authors proposed a new criterion, which is to apply the IMS criterion to a subregion known as the physical Coulomb branch moduli space inside the naive Coulomb branch associated with the given EFT. Okay, and this physical subregion is defined such that the monopole string has positive tension everywhere in the physical region in the given EFT description, and the incident particles have positive mass everywhere except at the origin, okay, where the CFT lives. And this generalized criterion, the quivers are saved, okay, and they also carried out the general classification of supposedly consistent single node gauge theories in 5 dimensions that can have 5D into 1 superconformal field theory as the UV completion. Okay, and this give a larger list beyond the ones that are classified by this IMS paper. Okay, and then there's as this already mentioned. So as an application of this new criterion, you can reclassify many of these effective theories, which can have superconformal completions. And later, but these are kind of a bottom-up approach. So you start from effective theory, just like what Philip Argyris and the collaborators have done in 4 dimensions. This is an analogous approach in 5 dimensions. But you can still ask, is this a sufficient condition, right? So to know that whether it's a sufficient condition, one quick way to do that is to give a UV completion of this effective field theory that knows directly about the superconformal fixed point. Okay, there are many possible ways to UV complete, mostly coming from M theory constructions, or 60 coming from F theory construction, but compacted from the circle with possibly twists. Okay, and explained in this recent paper, this nice recent paper, some of these theories that are classified by these authors do have UV completions coming from M theory, but some don't. Okay, so this means that we probably need a more complete criterion. That's one possibility. So the conditions described here are not sufficient. Okay, we need some more criterion. But another possibility would be that there may be also other kind of UV constructions that's not considered in this paper that gave rise to single node theories. Okay, maybe later experts can comment on these possibilities. Okay, so let's. Yes.
Like a minority, the ones that don't, or
there's a list. I didn't count. There's a list. It's not 1 or 2.
I see.
Yeah, and maybe someone in the audience knows the number better.
Okay. Thanks.
Okay. Yeah, no problem. All right. So just to give you a flavor of what kind of UV complete description there are, let me just describe one. I mean, Fabio already described very nicely the PQ brane construction. I'll describe another one, which is coming from M theory, which is related to the PQ brane construction in certain cases, which I'll mention. So just to say again, this subtleties with the EFT constructions, like what kind of criterion we should impose, it makes it very important to have a UV complete description of these CFTs. Okay, and here it will be coming from M theory. So as you remember, in the context of 14.2, a natural way to construct superconformal field theories is to have your string theory, M theory, probing a threefold Calabi-Yau singularity. Okay, so in this case, because we're looking for 5-dimensional theory, the context will be M theory on the Calabi-Yau threefold singularity, and more precisely, it's so-called canonical singularity. This is just for the expert; it's not important for the rest of the discussion, really. The details are explained in many papers, and here it's a subset of the references, of the many references here. In this geometric setup, the fact that you have this non-compact Calabi-Yau allows you to decouple gravity such that the effective dynamics in the Lagrange are just captured by some effective theory on this 5-dimensional transverse space-time. And the fact that it's singular, meaning that you are collapsing various surfaces and curves inside X, removing all the possible scales, indicates that you end up with actually a superconformal theory in IR. The reason is supersymmetry is, of course, coming from the threefold singular, where it satisfies some Calabi-Yau condition. So in this geometric setup, you can ask what kind of geometric quantity correspond to the deformations that you can deformational CFT which we described from the EFT perspective. So the first deformation that in the EFT perspective, important in the EFT perspective are these Coulomb branch parameters, phi I, the bottom, the scalar component of the phi D1 into one vector multiplets. They correspond to, they parameterize the Krapin resolution of this Calabi-Yau singularity. Okay, so that keeps the Calabi-Yau condition. That's why I give you to supersymmetric vacua in the 5D effective theory. Okay, and the CFT is recovered when you collapse all these curves and surfaces. Okay, so I used X bar to denote the resolved threefold singularity. And more, a slightly less discussed quantity are the Higgs branch coming associated with the threefold singularity, and they correspond to complex structure deformations of the singularity. Okay, so in the rest of the talk, I'll mostly focus on the Coulomb branch. Geometrically, the full Coulomb branch, including possibly mass deformations, correspond to the extended Kähler cone associated with the threefold singularity. And there are various walls in this extended Kähler cone where the Calabi-Yau metric may degenerate. Okay, and there are also different chambers that relate by flop, which Fabio also mentioned from the PQ brane perspective last talk. And they physically correspond to changing the mass of some hypermultiplets. Okay, and this threefold singularities can typically be modeled as a collection of complex surfaces, homomorphic surfaces, or a neighborhood of these homomorphic surfaces, also known as divisors. And there are compact divisors in this collection, and there are also non-compact divisors. And if you take the point query dual, they give rise to in the threefold, they give rise to two forms on this resolved singularity. And this applies to both the compact divisors and non-compact divisors. Okay, and using the harmonic representative of these two forms, you can expand your M theory three form into these harmonic two forms, and the coefficient will correspond to the dynamical U1 gauge field in your EFT. And if you expand in terms of this harmonic two forms that are due to non-compact divisors, you get background gauge field associated with the possible flavor symmetries. Okay, and as I mentioned, the EFT at the 2D level is just determined by prepotential. So you may ask, how is prepotential encoded in the geometry? And it's encoded in a very simple way. So the Kähler form of the threefold singularity can be expanded into this harmonic two forms, and the coefficients again would correspond to the scalars that parameterize the Coulomb branch of the 5D effective theory. And then the prepotential, so you can include this background 5D into one scalars as well, which will correspond to mass parameters and possibly gauge couplings if you have gauge theory phase in IR. And the prepotential is simply given by the volume of this resolved Calabi-Yau manifold, sorry, the resolved Calabi-Yau singularity. And because of the and this volume can also be written as the integral of the Kähler form raised to the third power. And if you write in terminal divisors, it's essentially the intersection number of the divisors on the resolved threefold singularity. And as we mentioned, there are various important BPS objects and BPS states on the Coulomb branch. So there could be BPS particles, there can be BPS strings, and they also have very natural descriptions in terms of branes wrapping various cycles in the threefold singularity after resolution. So that have finite mass, non-zero mass. In particular, the M2 branes wrapping various holomorphic curves on the resolved threefold singularity give rise to BPS particles, while M5 branes wrapping surfaces, divisors, give rise to multiple strings, and there will be non-trivial bound states between these objects. And just want to emphasize here is that the BPS particles here includes instantons, and this is something I want to emphasize again, is that the geometry does not distinguish between perturbative versus non-perturbative BPS particles. They're all coming from M2 branes. It's only after you chose a specific frame in the EFT description there's a distinction between perturbative versus non-perturbative particles. Okay, but everything is on the same footing from M theory, and this is also why it knows more about the effective theory, the effective prepotential, which is intrinsically perturbative in one description. Okay, and as I mentioned, there's a close relation between the M theory construction and the PQ brain web construction that Fabio described in detail. So in particular, this relation can be made quite explicit if this threefold singularity is toric. Okay, and in that case, by compactifying the M theory construction on the transverse circle inside R5, 1, and do a T-duality on the circle in the singularity along the x directions, one of the x directions, you can obtain this PQ web diagram for the type 2B. And operationally, that corresponds to taking the toric diagram that describe this threefold singularity and take the dual diagram, and that will be correspond to the PQ web diagram describing the same 5-dimensional superconformal field theory upon possible deformations. Okay, and this is the example. Oops. Okay, and this is the example for this so-called E1 tilde theory, which we'll talk about later. Okay, so let's now come to the examples. So a particular nice set of examples of threefold singularity that was studied in the early days of 5-into-1 theories by Seiberg and Morrison is this following singularity. Okay, so it's a singularity that's engineered by a neighborhood of this so-called Del Pezzo surface, which is coming from blowing up points on P2, and the total space can be thought of as a vibration of this canonical bundle over this Del Pezzo surface. Okay, such that the Clavier condition is satisfied. It's also known as the local Del Pezzo singularity. Okay. This as was explained in the paper from Seiberg and Morrison, this threefold singularity in M theory engineers this ENF plus 1 SCFTs, which I talked about before, with a Coulomb branch description that's coming from SU2 super Amuse theory coupled to NF, a fundamental hypermultiplex. Okay, these are also sometimes referred to as the simplest, thought of as the simplest rank 1 5D superconformal field theories. Okay. So, for example, in a DP1 case, so there's something with the terminology. So there's something funny with terminology because there are two possibilities. So I will just put a quotation mark here. This will correspond to some theory with right. So there are two possibilities. One possibility will be this F0 surface, which is essentially P1 times P1. In this case, the resulting CFT engineered by this kind of singularity is the so-called E1 SCFT. It has SU2 global symmetry, okay? And on the Coulomb branch, it's described by SU2, just a single SU2 super Amuse without any matter content. So as I mentioned before, any super Amuse theory in this effective theory description has a U1 to Bordeaux symmetry, okay? So this description makes manifest the U1 to Bordeaux symmetry, but that U1 to Bordeaux symmetry is enhanced to SU2 at the superconformal fixed point. So this just answering again one of the questions that I asked earlier. And there's also a close cousin of this, interestingly, known as the E1 tilde SCFT. This CFT, however, only has U1 global symmetry, and the effective description upon a mass deformation is described by also SU2 super Amuse, but interestingly differed from this other super Amuse by a discrete theta angle. This discrete theta angle essentially corresponds to the fourth homotopy group of the gauge group SU2. There's a Z2 discrete theta angle, and this is analogous to the 4-dimensional theta angles. But in that case, it's continuous. It's a real number, but here it's discrete. Okay. And more generally, for the other Del Pezzo surfaces, give rise to this ENF plus 1 Seiberg-Morrison type theories with various flavor symmetry groups. In all cases, they are enhanced from the manifest symmetry on the Coulomb branch, which always involves some U1 factor. Okay, just want to emphasize here that most of this Del Pezzo surfaces are not toric, so there's no well, maybe experts know, but I don't know any PQ web diagram realization of this. For example, for this NF bigger than 3, bigger or equal to 3. Okay, so these are non-toric. But you can still use the M theory description to extract the EFT description for this theories. There's a question. There are webs for this. Okay, I see. Thanks. Right. So the geometry of this is so the F1 is essentially with what I've drawn here. This is the PQ web diagram, and this is toric, and this is related to the P1 times. This is and this sorry, F0 is P1 times P1. So this is different. So this F1 is like a non-trivial vibration of P1 over P1. So there are different geometries, and this corresponds to the turning on the discrete theta angle in the effective theory.
So I guess my question is that usually, like what sort of change in geometry effectively produces this theta angle?
I think you have to go through some dualities, and you can relate to some discrete flux in the background.
Okay, I see.
Yeah. Right. There's a yeah. So there's another question. So U0 on P2. Yeah, that's another CFT. That's the CFT. That's a very interesting CFT with no flavor symmetry. And on the Coulomb branch is described by U1 Chern-Simons theory as opposed to SU2 gauge theory. And it's described by, I think, first by the paper by Seiberg and Morrison. Okay. So that's a candidate for like a simplest, well, the minimal 5D superconformal field theory. Okay. And yeah. Okay. And the deformations. So the deformations of this singularity. So as I mentioned, the complex structure deformation will correspond to the Higgs range of the CFT. And because of this theories, this Seiberg-Morrison theory turns out to have very interesting Higgs branches. They're given by the one incident moduli space associated with this Lie groups. And their dimension is given by the 2 constant number minus 1. Okay. And when this is not simple, you're supposed to take the sum. Okay. And this is explained in the paper from Seiberg and Morrison. But I don't know to what extent general complex deformations of toric manifolds are understood. Maybe something later for discussion. Okay, so that's all I'm going to say about the M theory construction. Let's now move on to some CFT observables that you can extract. So some of the important CFT observables that you can extract from various setups that relies on supersymmetry, and these are the protected operators. The protected operators in the 5D into 1 are classified by studying the representation theory of the superconformal algebra F4. And the protected ones are actually the half BPS superconformal multiplets. And they are in one-to-one correspondence with the Higgs branch Carl ring generators, where in which case their scaling dimension is 2 times the SU2R spin.
Yifan, there are a couple of questions.
There are more questions?
Chat.
Right. Yes. Thanks, Cyril. Yes. I mean the theta angle will break CP. Yes. Yeah. So I think that's partly the problem. I mean, when you want to characterize the full Higgs branch, you're supposed to consider general complex deformations, and that may not give you a toric manifold anymore. But I think for EN theories, as Dave was saying, that's always true. Okay. Thanks for the questions. And among these Higgs branch Carl ring generators, some of the very important ones are the ones that carry. So typically, because these are protected operators, you can try to extract them from the EFT or from the geometry. Okay. without knowing about the details of geometry, like the explicit metric, which is very difficult. But from the effective field theory approach, an important subset of these operators are the ones that carry non-trivial U1 topological charge. These are also known as the EFT instanton operators. And these operators are very important because they basically give rise to the symmetry enhancement, which happens very often in 5D context. And this is very analogous to the monopole operators that give rise to symmetry enhancement in 3D context. But in that context, it follows from UV to the CFT and the IR. Okay, there are many papers. I've just listed one, but yeah, there are many papers. I'm sorry for missing many references here. More generally, there are also 1H BPS operators, which is beyond the EFT description, but still captured by which is beyond the EFT description, but some combination of them can be still captured by some information about the EFT. And these combinations are captured by the so-called Superconformal index, which counts signed combinations of multiplets containing 1H BPS operators. And the Superconformal index can be thought of as a weighting index defined for the Hilbert space in this case S4. Okay, so you're supposed to do radial quantization, and this is essentially the weighting index on S4, weighted by various fugacities that commutes with the supercharge that you use to define the weighting index, which I've taken to be Q and its conjugate here. So these are some fugacities associated with the rotation symmetry on the S4, as well as R symmetry and potentially other global symmetry global symmetry charges. Okay. And the insertion of this fermion number, as you may have remembered from the weighting index construction, make sure that this index only receives contribution from 1A BPS operators. Okay, and this index is and this kind of feature. This index has this protective feature that is computable using the IR gauge theory. Okay? Essentially, it's a free field computation. And this is the consequence that it's protected against interactions. Okay. Right. What about so far that's about the operator spectrum. What about correlation functions of local operators, which is also very important in specifying the basic data of a superconformal field theory or any conformal field theory. So the most basic kind of local correlation functions are 2-point functions of conserved currents, such as stress tensor, which you have in any conformal field theory, and also conserved currents if you have a global symmetry. Okay. The 2-point function of stress tensor, 2-point function of conserved currents, all the position dependence are completely fixed by conformal symmetry. There's some structure that depend on the positions. But what's physically important are the coefficients, CT and CJ, which I'll call CT and CJ here. Okay, and this stress tensor and currents are canonically normalized, so these coefficients can be completely unambiguous. Okay, and in some sense, these coefficients, because they're 2-point function of stress tensor and the conserved currents, they're like basic characterization of the number of degrees freedom in your theory, or for the CJ, it's like number of charge degrees freedom in your theory. Okay, and in this sense, they're analogous to the conformal and the flavor center charge that you encounter in even dimensions. Okay, in those cases, the 2-point function can be also related to combinations of the usual conformal and flavor center charges. So how do we compute this kind of quantities for this for the fixed point? Can we do that from the EFT, from the IR gauge theory? Okay. That sounds very difficult because you want to compute some non-protected 2-point functions. Okay. But if you just formulate the problem at a fixed point, you can see that these 2-point functions can be obtained by some deformed free energy of the fixed point. So in other words, if you start from the free energy of the theory on of the conformal fixed point theory on S5, and you turn on some mass deformation and squashing deformation that couple to the flavor symmetries and the squashing coupled to the stress tensors, naturally, if you expand them in the small squashing or mass parameters, the quadratic terms would split out the coefficients, which are proportional to CT and CJ. Okay. So this is just to translate the problem into computing the deformed free energy of the fixed point, which is still a very hard problem. But thankfully, because of supersymmetry, one can hope to compute the same deformed free energy using the IR gauge theory. Okay, so you can ask whether this is the same as the IR gauge theory. And luckily, this is the case, but up to some subtle counterterms. And this is the consequence of, so the reason they're almost the same is thanks to supersymmetric non-renormalization theorem. And but they can differ by counterterms, which can be analyzed in this paper, as in this paper. Okay, so once you establish this equality, so in particular, this counterterms do not affect this coefficients. So that's very important, but as addressed in this paper. If it affects the counterterm affect this coefficients, then you're doomed. You can carry out the analysis. Okay, so then you can just use various known results to compute this free energy. There's a very nice paper that described this from geometric setup in 2012. And then this free energy takes the following form. This free energy takes the following form. So this is actually e to the minus f. Okay. It's an integral over the Coulomb branch, the real Coulomb branch of the 5D IR gauge theory, and the integrand involves this effective potential on the Coulomb branch, which we discussed previously, and there's some non-perturbative contributions. Okay, so as I said, to recover the fixed point, it's very important to keep track of how the how this non-perturbative degree theorem like instantaneous and massive multiple strings become massless as you approach the CFD, and these are the things that keep track of these contributions. And there are 3 factors of them. Okay, as opposed to what happens in 4 dimension, if you remember Pastel's localization formula. Okay. This factorization is explained in this paper. And with this very explicit formula, you can apply this to known IR gauge theory description of superconformal fixed points in 5 dimensions. For example, the Cyber-Morrison theories. And as explained in this paper, you can indeed directly compute this CT and CJ for these theories. Okay, and as a byproduct, you can check that symmetry enhancement is respected at the level of local coverage function. So what do I mean? So the IR gauge theory, as I said, makes manifest only a U1 times H subgroup of the full global symmetry. So as a consistency check of a symmetry enhancement, if you take 2 derivatives of the free energy respect to the mass parameter parameterizing the instant U1, and compare that with the 2 derivative of the free energy respect to the mass parameter coupled to the hypermultiplets, you better get the precise relation that's predicted by the enhancement of the U1 times H flavor symmetry to ENF plus 1, and that indeed works out in this procedure. Okay. So this is some additional evidence for symmetry enhancement beyond the superconformal index. All right. Okay. So let me now move on to 6D. So I'll not say too much about 6D because Fabio would give a very comprehensive perspective on them later in the afternoon. But let me just say some. Let me still say something. Okay? So as I mentioned before, there are 2 kinds of superconformal field theory in 6 dimensions. Okay, there's the 62,0 theory, which has AD classification. Okay, the conformal symmetry group looks like follows. But there's a much larger class of 61,0 theories with half supersymmetry. In those cases, the arc symmetry group is reduced from SO5R to SU2R, and there's a very nice geometric classification from F theory, known as the atomic classification. To my knowledge, in this very nice paper, but to my knowledge, we don't yet know whether this is a complete set of inconsistent 1,0 superconformal field theories. Okay. In particular, whether there are theories with no tensor branch, which we'll come to in the end. So let's now assume that the theory has this nice tensor branch, as in this F theory constructions, and talk about the effective theory on the tensor branch. Okay, just to remind you, the basic degree freedom possible free fields that I can use to write the effective theory are tensor multiplets. Okay, which includes this scalar field phi and some self-to-2 form B and the fermion chi. Okay, that transform as a doublet under SU2R. This minus means negative chirality and plus means positive chirality. Okay, the fact that you have the scalar give rise to this tensor branch, And this is something that's mysterious from the CFT perspective, but otherwise is manifest from the geometric construction from F theory. It is the moduli space of the CFT. But the CFT, direct CFT understanding of this emergence of this moduli space is still missing. Okay. There's also hypermultiplets, which is very similar to what we have encountered in 4 and 5 dimensions. They contain some scalar transformed as doublet on the SU2R and some fermions. And they give rise to the Higgs branch that's very similar to 4 and 5 dimensions. In addition to this basic fields, you also have this vector multiplets. And importantly, the vector multiplets in 6 dimension doesn't have any scalar, okay? So it doesn't give rise to some additional branch on your moduli space. And this is related to the absence of mass deformations in 61,0 theory, because mass deformation can be thought of coupling to some background vector multiplet. And if your background vector multiplet has a bottom component that's a scalar, that could be the mass parameter, but not in 60. Okay. And as was already mentioned in Cantaro's talk, also reviewed in Fabio's talk, the effective theory action at 2D level takes a very simple form as follows. And this is emphasized again, this is some pseudo action because the B field is supposed to be self-dual, and the self-duality is understood as imposed at the level of equation motion. Okay, and there are also various background couplings between the self-dual 2 form, to background gauge field and background, curvature tensors on the tangent bundle, and which I'm suppressed here. Okay, which are important for computing various anomalies using the effective theory description that Cantaro reviewed. Okay, so what are some BPS states in this 60 effective that can be described in the 60 effective theory? So there are this self-dual strings. They are 1 + 1 dimensional. They're also known as the instanton strings in the sense that they're similar to instanton particles and instanton gauge theory instantons in 4 dimensions. They're called dimension 4. They support some transverse flux for either it can be dynamical gauge field on the tensor branch associated with the vector multiplets, or it could also be some 4-form flux. Sorry, some 4-form charge density associated with background R symmetry, and also some Poincare eigenclass for the tangent bundle. Okay. And this the fact that this string is 1 + 1 dimension means that it can carry non-trivial perturbative 12 anomalies, okay, on the tensor branch. And the relevant symmetry here, which can have 12 anomalies, consists of flavor symmetries of your theory, gauge symmetries on your tensor branch in the tensor branch effect EFT, SU2R symmetries, as well as the transfer rotation to the to the string in the 60 spacetime. Okay. I leave it again as an exercise for you to show that the strings preserve 0,4 supersymmetry. You can analyze. You can obtain that by analyzing the central extension of the 61,0 supersymmetry algebra. And these 12 anomalies, importantly, can be computed from anomaly inflow, just like Cantaro explained how the 12 anomaly associated with 1,0 theories can be computed, engineered by brains, can be computed by anomaly inflow. They explain this very nice papers. And this 12 anomalies carry various information. I mean, these are anomalies on the BPS strings, but it knows about, as you expect, it knows about the full theory. For example, it gives strong evidence for the AD classification of the 2,0 theory because the structure of essentially the structure of the tensor branch is encoded in the anomaly polynomial of the string. And they also give rise to evidence for the emergent EA global symmetry in the case of E-string theory. And there's many other physical quantities, physical information you can extract from these anomalies. Okay, and I should also comment that there's a very much related object in the 1,0 theory that are non-dynamical BPS strings, also known as the surface defects. Okay? And there's also very nice work on in those directions. Okay, that preserve the same supersymmetry, but they are non-dynamical and should be thought of as defects. Okay, so what are some examples of CFT observables that we can extract from the EFT or from the geometry? So first of all, there are, again, is half BPS operators, just like what happens in the 5D and Duan case. And they correspond to the Higgs branch carry ring once again. And there are scalar operators whose dimension is determined by the SU2R charge, just like what happens in 5 dimension. And as I mentioned many times, the Higgs branch is very nice in the sense that it's kind of uniform across dimensions because of supersymmetric non-randomization theorems In particular, in these various theories, upon computation from 6D to 5D to 4D, the Higgs range is typically preserved, also down to 3D. Okay, if you go to 2D, something like that happens, but I'll not talk about it here. And once again, there are also more non-supersymmetric operators which you can extract from the effective theory potentially. These are 1/8 BPS operators, which are again captured by the superconformal index. Okay. So these are operators preserved by supercharge in this complex conjugate. But unfortunately, unlike the 5D case, we only have limited knowledge for this superconformal index. That's because the tensor branch theory is simple, but the superconformal index receives non-trivial contribution from the self-dual strings on the tensor branch. And so far, there have been only limited information about the self-dual string contributions, and it's revealed in this paper. And there's some recent development for specific theories like E-string theory. Okay. What about beyond the operator spectrum? So what about local correlation functions? So in this case, one kind of a nice technique to study correlation functions in general is the superconformal bootstrap program, which I'll say a few things. So here, what one can study is the 4-point function. 4-point function of half BPS Higgs range primaries. So the same operators, but you study their 4-point functions. So the Higgs range operators also, so here I want to focus on the particular case where the Higgs range operators correspond to the moment map operators, because in 6 dimension has scaling dimension 4. So the 4-point function can be written as follows. It has some position dependence where it encodes information about the insertion of each operator, and there's some R-symmetry polarization that keep track of the R-symmetry polarization. And this 4-point function is restricted by conformal symmetry to take the following form. There's some universal factor that you can strip off, and the non-trivial dependence is coming from this factor that depend on the conformal cross ratio, which are invariants of the residual conformal symmetry, as well as some R-symmetry cross ratio, which is analogous to the conformal cross ratio. And these moment map operators are special in the sense that they contain conserved currents as conformal descendants. Okay. So the bootstrap problem that and the general way to attack this 4-point function is to explore constraints from unitarity and crossing, which says that when you factorize this 4-point function in different channels, you better get the same results. And that leads to various constraints between the OPE coefficients and operator spectrum. That's beyond the supersymmetric quantities, okay? And in particular, in this case, the bootstrap problem you want to study is the 4-point function in some 61,0 theory with a fixed global symmetry. And these O's are the moment map for those global symmetry, which I'll call G flavor. Okay. And then if you run the bootstrap machine, which is like a numerical black box, what you get is some bounds on the OPE data that appear in the OPE channels. Okay. In particular, what appears universally in this 4-point function are the 2-point function of the stress tensor, which is related in this case to the conformal anomaly. One of the conformal anomaly coefficient in 61,0 theory is proposed to C3 up to a positive number among the 4 conformal anomalies in 61,0 theory. And then also the CJ, which is related to the current central charge in this case. Okay, so in this case, what the bootstrap box produced for you is as I explained this. Okay, I forgot to write the reference. The paper from Chen and Lin. Okay, I think it's 1.7. Okay, I need to double check. But in any case, so here the bootstrap problem, bootstrap box produced for you is some bounds on this center charges, conformal and flavor center charges. And in the particular case, applied to moment map operator generate the EA flavor symmetry. So this is some putative CFT with EA flavor symmetry. What one finds that this bound is precisely saturated by the E-string theory with EA, which has EA flavor symmetry. So what this means is that this is the EA theory is likely the minimal 6E SCFT 1,0 SCFT with E8 symmetry. Okay, as you know, there are many examples in F theory construction or M5, M9 construction with E8 flavor symmetry, but E8 would have to be the minimal. Have to be the one with the minimal center charges with that property. Okay, And something also special happens. Something special also happens for the case when you have 2,0 supersymmetry. So in the 2,0 case, there's a very nice subsector of the full operator algebra, which can be characterized exactly. Okay? These are certain 1/4 BPS operators in the 2,0 theory, and they form a closed subsector of the full operator algebra when you restrict them to plane inside the 6-dimensional spacetime. And they generate the chiral algebra in the sense that there's non-trivial dependence on the holomorphic coordinates on this plane. And the structure of this operator algebra is equivalent to that of a W algebra labeled by this AD Lie algebra that labels the 2,0 theory. Okay, this is a very nice paper appeared in 2014. Okay. Okay, so since I'm going pretty fast here, so that's actually all I'm gonna say about the 6D. So let me just give you a summary of what I've talked about so far, and some connected to something that the Fabio talked about so in earlier lecture, as well as later probably later today, is that we have this various relations between geometry and CFTs, and we also have relations between various CFTs in different dimensions. I think I didn't have time to talk about, but Fabio would talk about in some aspects of them. For example, we have this 60 in 60. We have the 1,0 theory and 2,0 theory. This theory is engineered by F theory, in general, probing some elliptic singularity. So this is what typically happens is if you in the pure geometric setup, the CFT is coming from some F theory, M theory, or type 2B from string theory probing some singularity. Okay? So for example, in 6D is coming from M theory probing elliptic singularities. In 5D is coming from M theory probing canonical singularities. And in 4D, they're coming from type 2B, probing some rational so-called Gorenstein graded singularities. Graded means there's a C-star charge, okay? C-star symmetry, scaling symmetry that's required for conformal invariance. But on the other hand, there are also brane constructions for each of these theories. So this is the incomplete, but for example, for 6D, there are constructions from M theory using branes like M5, M9, also in the presence of overflow singularities. And for the 5D, there's this PQ-Web diagram, in addition to type A realizations related to the M theory. There's a PQ-Web diagram that Fabio described in length. And in 4D, you can again connect to F theory by considering branes in addition to singularities, like D3 branes on top of D7 singularities engineered by D7 brane, as well as with additional S-fold. Okay, this is discussing some recent paper from I think from Fabio and Sakura and collaborators. And as I mentioned, these theories themselves, just at the field theory level, are also related to one another by compactifications. So for example, if you can compactify the 6D theory on the circle, possibly with some twist, like in the 2,0 case, you can twist by the outer automorphism, and possibly with mass deformations, okay? But you want to make sure that preserve the 5D into 1 supersymmetry, and this way you can engineer 5D theory starting from the known class of 61,0 theory. So this gives you another organized principle. So in addition to the organization principle coming from singularities or brane webs for the CFTs, there's another organization principle coming from just the full set of 61,0 theories. That organization principle works by doing compactifications with various decorations you can do. And moreover, you can also do the same thing going down from 5 to 4, okay? Again, some complication with possible twists. And
I have two questions.
Yes.
So
yes.
First thing is that in going from 6D to 5D, you have added some mass deformation, but you also said that 6D theories don't have a mass deformation.
Oh, sorry. Here it's like a you should think about it as holonomies. Sorry, I think it's a massive deformation, but it's really holonomy. Okay, let me just. So for example, one way to get to the E8 submersion theory from 6th dimension is to compactify E string by turning on some holonomy.
I see. And so is that holonomy for so is that a holonomy for some discrete symmetry, or is that so yeah, what symmetry of 6th dimensional theory are?
Global symmetry. They're global symmetry. They're holonomy for the global symmetries. So this is like a flavor Wilson line, if you wish.
Okay, I see. And then in going from 5 dimensions to 4 dimensions, do we compactify on a circle with twist or without twist?
You can do twist, or you can do without twist.
Okay.
Yeah, there are various options. I'm not sure if the full set of games you can play in either case is completely known. Okay. Also, the same applies if you want to go directly from 4 and to 6 to 4. There are also various games you can play. There are more games you can play if you want to preserve less supersymmetry, like 14 to 1.
I see. I see. Thank you.
Mm-hmm. Thanks for the question. So yes, so from 6, as I mentioned, you can also go directly from 6 to 4. That give rise to more bigger class of games you can play. Class S construction, generalized class S construction with various kinds of functors. Okay, and there's also this strictly speaking, the class S applies to the 2,0 case, but there are also some generalization to the 1,0 case that have encoded 2 supersymmetry in there. Okay, so that's the summary. But let me just emphasize again this general philosophy that I've been trying to emphasize in these talks. So there are 3 important objects which have important interplays between one another. One is the CFT. The other is the EFT, which is an effective description that captures various deformation of the superconformal fixed point. Okay. And the other is the geometry, which typically gives some UV complete description. Okay. There are various relations between them. Let me just emphasize a few. The existence of superconformal field theory as a UV completion of a EFT greatly constrains the kind of EFT you can write down. We don't yet understand the complete set of consistent condition on the EFT, such that have a SCFT construction. But in practice, how we proceed is that we get some constraints and we classify the kind of theory that obeys those constraints, and they give some candidate SCFTs. Not all of these candidates will have UV completions. And how do we know? Quite an efficient way to do that is to use geometry. Geometry gave us manifestly UV complete descriptions, and they also gave us some geometric classifications. And whenever we see there are examples here, candidate examples here, which are not realized with geometry, we think harder about the EFT, and we can see if we have missed some additional conditions. Okay, and if we do not, that means that the geometric construction may not be complete. So that means that we need to include more ingredients in the geometric construction, and this leads to many. I mean, this is like a positive feedback that leads to development in all these areas. Okay, and so by good theories, I mean the ones that have geometric descriptions. Okay, and also if the bootstrap machine. I mean, the bootstrap machine promises you to solve the SCFT if you're powerful enough. It involves an infinite number of crossing equations to solve. But if one day someone or some computer or some robot is powerful enough, it can solve fully the SCFT, then you can potentially use the SCFT to bootstrap the geometry, in the sense that so far we have been focusing on like BPS quantities, supersymmetric quantities from the geometry. But the SCFT knows much more about these BPS quantities. For example, knows about the spectrum of the non-BPS operators, and now will be associated with various volumes in the geometry that's not associated with supersymmetric cycles, for example. Okay, there's some application. There's some potential application already in the 2D CFT context, but yeah, but they're similar in higher dimensions. Okay, so let me now come to the end where I will give you some open questions relevant for this discussion of 5D and 6D superconformal field theory. First of all, as I emphasized a few times, it will be very nice to have some more complete, like necessary sufficient EFT criterion for the existence of a UV fixed point in 5 and 6 dimensions. Okay, so beyond the ones that we already know. Okay. And this will be useful to pursue some classification of these theories from field theoretic methods. And another thing that I find interesting is a notion of a 5D F theorem. Okay, so in 4 and 6 dimensions, there are proof for the A theorem, thanks to the work of Schremer and Komagowski in 4 dimension, and 6 dimension. There's some nice results from Clay, Thomas, and Ken. But in 5 dimension, F theorem still seems open. There are some evidences for the flows between the E and F plus 1 theories, but we don't yet have a general argument for this even in the 5D into 1 context. Okay, And then another important question that I think is another question I think is very important is to understand this notion of 5D moduli space, the Coulomb branch, and the 6D tensor branch directly from the CFT perspective. So there's, in this case, there's no protected operators who would trigger, whose valve parameterize this moduli spaces, which you see very nicely from the geometry coming from resolutions. So how do we understand them from the CFT perspective? Okay. And then it will be nice to understand some notion of a minimal or endpoint of non-trivial endpoint of RG flows in 5D and 6D, which should be characterized some kind of a minimal CFTs. Perhaps CFTs with no tensor branch or Coulomb branch, which is certainly minimal in one sense. It'll also be interesting. Various anomalies of these theories, 6D theories, has been already solved by an inflow method, preserved anomalies. But it'll also be interesting. Many of the theories also has higher form, in particular discrete symmetries, and it'll be interesting to study their anomalies. Okay. And this is there's some very nice recent paper that address this in both 5D and 6D. Okay, and in particular, it'll be interesting to understand how anomaly matching upon compactification, but by one dimension rather than on the Riemann surface. For example, anomaly matching between 6D on the circle and 5D. Okay, so then we can maybe use the many results for 6D anomalies to understand 5D anomalies. Okay, which is not existent for the traditional TOF anomalies, but maybe for the higher symmetry anomalies. Okay, so with that, I'll end, and thank you for listening, and please stay healthy.
Thank you very much, Yifan. Let's thank Yifan for the great set of lectures, very informative. Thank you very much.
Thank you.
Okay, any questions? You should have finished with point number 7, not 6. 6 we know exists.
Oh. Sorry?
Any questions?
You said earlier on that 't anomaly in 6-dimensional theories comes from BPS strings. In what sense is that statement true?
So that's not what I meant. I meant there are anomalies on the world sheet of BPS strings in 6 dimensions.
I see, but what's the theory that's living on those BPS strings?
So on the tensor branch, you can characterize, because the tensor branch there's some essentially free description, in terms of vectors, tensors. So you can characterize the world volume theory of this BPS string by realizing what kind of symmetry. What kind of first figure out the Goldstone modes associated with the symmetry that's broken, and you can also figure this out by the brain description. So there's some various hypermultiplets coming from the brain, coming from the in a type 2B, coming from strings attached between this brain that engineered this BPS string, and also the brain that engineers the 6D theory, things like this.
I see. Is there a reference?
Yeah, so I gave the reference here. Yeah.
Oh, okay.
So you can compute these anomalies using the field content. You can also compute it more generally using the anomaly inflow, and both perspectives are explained in this paper. So there are also other papers, I should say.
So this anomaly for the world sheet theory is different from the sort of the bulk gauge flavor SU2R symmetry anomalies. Like there could be.
It's different. Yeah, there's a contribution from the inflow from the bulk, but there are also contribution from inflow from the bigger bulk coming in here. Yeah.
Okay.
Right. These are anomalies on the world bottom. That's
right. Also, how much can the knowledge of like 4D n equals 2 as CFTs help us learn about learn about 5D n equals 1? Like we know that we can compact it, and we also go up somewhat.
Yeah. So there's a notion of a 5D subweighting geometry, which is coming from the 5D theory on S1.
Okay.
So yeah, you can try to use that. I'm not sure to what extent it's explored.
Okay, so would 4D SCFTs, are there examples of 4D SCFTs that lift to 5D SCFTs?
Yeah, yeah. I mean, but the right. Yeah, because for example, the subordination theory, the E6, E7, E8 are closely related to the Minahan-Nemeshensky theory.
I see.
By comparative additional circle. But in that case, you don't need to turn on any twist. The Higgs range are identical, and the theories are actually related by comparative the circle and do a mirror symmetry.
And are there also examples of 4D SCFTs that, for which it's necessarily known that there is no 5D SCFT lift?
That I don't know. Yeah, because 4D is a huge zoo. I mean, yeah. I won't be surprised if you can find. Well, okay, but that's against the lore in the literature. So in the literature, I think people tend to believe that all the 4D, 5D CFTs would have some 6D uplift as some SCFT. Yeah, it's a lore. Yeah, so it's kind of a unification picture, but because we don't know yet the full set of 6D SCFTs, I guess that's open yet. So for example, this theory I mentioned in 3 dimension, not in 4 dimension, the 3D into 4 theory, which has same supersymmetry as 4D into 2, 5D into 1, and 61,0, but it doesn't have a Higgs branch or nor a Coulomb branch. Does that theory has a lift? I guess that's another question you can ask.
I see. Yeah, one last question would be that what are the global symmetries of the 62,0 theory with they have ADE classification?
Yeah, so the 2,0 theory as a 2,0 superconformal field theory doesn't have any global symmetry. But if you think about as a 1,0 theory has a SU2 global symmetry, just because SO5R symmetry splits.
I see. So when we compactify on the 62,0 theory in a circle with a twist, what global symmetry? So it seems like there's no global symmetry.
Yeah. So I was just talking about the continuous global symmetry, but there are some global symmetry that's discrete, that's coming from the outer automorphism group of the corresponding Lie algebras. So for example, for A2n, I mean AN, you have the Z2, which acts differently whether depending is even or odd, and for D4 you have this S3 as well.
I see.
And that's how you, for example, that's how you engineer 4D into 4 with non-simply laced gauge group, is to do such twist upon compactification of 62,0 theory on torus.
I see.
Yeah.
Thank you.
Yeah, no problem. Thanks for the question.
So there is another question in the chat. Is there a way to see the D equals 4 and equals 3 theory to lift to a higher dimensional SCFT?
Good question. Good question. Well, I haven't studied this, but I don't see why this is impossible. I mean, symmetry enhancement, for example, I mean, from 1,0, or possibly from 2,0. So this is equivalent to ask whether there's a class S. I mean, okay, not quite equivalent, but one question one can ask is there a class S construction for 4D into 3? For the non-trivial ones, not the ones coming from discrete gauging. Oh, there it is. I think Sakura.
So I think this is Iñaki and Diego's paper where they construct the n equals to 3 theories in 4D from M5 brains.
I see. But can I understand that as a class S, modified class S construction?
I think it's sort of like, you know, they call it a U-fold kind of background. I don't know whether you want to call it class S. But it's certainly coming from 6020.
I see. That would be nice to understand this directly from the 20.
But you mean n equal 2 classes? Do n equals 3 theories have n equal 2 preserving deformations? I thought they don't.
I mean, the abstract said the resulting setup generalizes the one used in the usual class S construction of 4D by using extra discrete symmetries on the M5 frame world volume. It'd be interesting. I didn't know this paper existed.
Yeah, I didn't know it. It's embarrassing. It's from quite a few years ago. Yeah, thank you for bringing up this reference.
Hi, related to this uplifting, do you expect that there's some source enhancement in 5D? Like
yeah, I mean the 5D you cannot, because there's only one possibility for superconformal. There's only one possible supersymmetry algebra for it to be compatible with the superconformal symmetry, just 5D into 1. Do you have in mind to? Yeah, so there's no possible further enhancement.
I mean, for example, you start with the n equal 1, and then you do some mass definition.
Yeah.
Totally SUSY, and then maybe in the IR, maybe I don't know, and just in analogue to the 4D n equal 2 case.
Oh, you mean, yeah, I mean, well, let's see. Well, the 4D into 2 case, there are 4D into 1 RG flows that flows to non-trivial 4D into 2 theories in IR. So maybe you're asking about 5D non-supersymmetric theory that has a supersymmetric completion. That's possible, but yes, that's beyond what can be captured by this supersymmetric effective theory, which I talked about.
Okay, thanks.
Yeah, it just there's a less freedom you can play with supersymmetry in 5 dimensions. There's only one. If you want conformal invariance, there's only one choice, unlike in 4 dimensions.
What about if you want to live to 6 dimensions? Say some n equal 1, yes, n equal 1 effective theory in 5D, which is UV completed by 6D by 2,0 theory.
Yeah, I think that's possible. I think maybe some works from Lecture and Gabby addresses this point, 2,0 with some supersymmetry breaking. Well, I don't remember what they did actually. But I think they engineered some 5D into 1 theory from 6D to 2,0 compactified on circle with outer twists. Some recent paper. Not sure if one of the authors is in the audience.
Yeah, I think those are only 5D n equals to 2.
5D into 2. I see. Yeah. Okay. So you don't know of a way to construct the 5D into 1 from 2,0 on the circle?
No, so if you don't have outer automorphism twist, you simply get the AD n equals to 2.
I know.
But if you have them, then you get other types of n equals to 2.
But there's nothing else you can play with. That's what I'm asking. One thing you can do is you can turn on holonomy for the R symmetry, right? You break the SO5 to SU2. So that's a possibility, but have you studied that? That cannot give you a 5D into 2 superamials with any gauge group.
So potentially that can, when you view it as a 1,0 theory?
Yeah, it's a holonomy, or in the 5D perspective, it's mass deformation. That's right.
So it turns out to mass deformation of the n equals to 2 theory. Yeah, so it will be n equals to 1 star.
Yeah, it's that's right. Yes, yeah. I see. But you say it doesn't have a 5D. It doesn't have a 5D UV completion. I guess that's your claim.
Yeah.
Okay.
Any more questions? If not, let's thank Yifan again for the wonderful set of lectures. And I remind you that on Friday, we will have a discussion session about all these topics and also about Fabio's topics. So please come and raise any concerns or ideas that you have. Okay, thank you very much, Yifan.
Thank you.
So we will meet in half an hour, in 35 minutes.